Welcome back. How things work. A few things now so the dust has settled a little on the first day. Just a few more logistical things, and then I'll ask you to ask me any questions you have remaining. The one thing that you do need for this class is access to the Wiley Plus Learning Spaces environment, which includes the book. So a paper book is great, 6 editions. The best choice for a paper book. 5th edition is very similar in print. Online, in the ebook, it's different. Things have evolved. So bottom line is make sure you purchase, obtain access to that online learning environment. Any of you who are in Physics 1060 and already purchased one of that access for the wrong edition, talk to me. We can fix it. Assignments. The first assignment, the thing that's really due, well, the first problem set is problem set 1, due September 7th. So it's still off in the future. You can pretend it doesn't exist. It's due at class time, and because of how that website works, it's just due then, 1 o'clock. Don't go past it. It's gone if you go past 1 o'clock on September 7th. Prior to September 7th, I think on September 5th, I assigned you to do the practice work associated with that first chapter of the book, the first 3 topics. Skating, which we're continuing today, falling balls, and ramps. This is an experiment for me because I've never had the ability to do this before. So I've assigned it, do the 5th. If that turns out to be hopeless, I can postpone it. I just don't want to have it. Maybe I can postpone. I have to think about it. But anyway, you should be reading the book. I'm tentatively assigning the sections in the book to be read. There are, in fact, no consequences to not reading it. So you can, if not required means don't do it, don't do it. Mary Royal?
Sorry. So when you're talking about the actions, how do you access it? So not the problem set, but the actions that go along with it.
There is a section within the book. So the question is, how do you access the practice material? Whenever you're looking at a chapter in the book, there is both the content, and then there's a section that says Orion, I believe, a tab. Click the tab of Orion. It's in there. There may be more direct links to that component. I haven't played around with it much myself. I mean, it's my book, but it takes a village to make this thing, and so there are parts of it that are like, oh my gosh, a lot of it originated from me in terms of writing the questions, I think I mentioned, but like how it ended up appearing is magic. So it's new to me too. If you get, and there is a chit-chat thing on it. I mentioned last time that I don't believe anyone started, but let's get a conversation going about things like this. Where the heck is, and how do you do that? And thanks for asking the first question. Other questions? Okay. Where we left off last time was the question. I'll flip back to it just so you can remember this thing. Remember this question about a rotary lawnmower and the reality that it can cut the grass even if the grass is not attached to the ground. This semester, you all made the most dramatic change I've ever seen, from 100% in favor of no, you can't cut it, to 100% in favor of yes, you can cut it, which is fine. What this tells us is that inertia is not really so obvious. It's not part of your intuition necessarily. Although you've heard your whole life this notion, an object at rest stays at rest, an object of motion continues in motion. I mean, that's just a truism of some sort. It's not really so obvious how it works. And so that's my goal in talking about skating, is to have you come away really feeling the concept of inertia. And it's all over the place. So this is an example, right? If the grass is sitting there minding its own business, literally sitting there, not rooted in, you can make it move by pushing on it, which is something we'll deal with very shortly. You can get it moving, but it tends to stay put. And you have to push on it to get it moving, and it's a process to get it moving. It doesn't just instantly go up to full speed and get out of your way. So you can basically smack at it in various ways. You can put a sharp knife through it. Yes, the knife does push on it. And question came up after class, someone really wanted me to go through that more carefully. Please ask it during class for those of you who get stuck on it and really want to tease it out. The other thing is that you all can teach each other better than I can how some of these new concepts work, because there's nothing like a person who has just learned an idea for the first time. They remember what they didn't understand. They know what they do understand. Such a person can be better at explaining it to a friend than I can, because I've forgotten the learning process. It was way back. So, to come back to the matter at hand, stuff sits there, tends to stay put, and you can muck with it for a while. You have to push on it for some amount of time to get it going. And so you can put a knife through it. The knife does push. It does begin to get out of the way, but it's too slow. The knife gets through it before it has a chance to basically get moving. You can punch it a punching bag. Nothing's holding it there. I mean, yeah, it's hanging on an attachment or something. But basically the fact that you can hit it and really ding it and hurt your hand, it has to do with the fact that it's got inertia. It tends to stay put. Snapping a paper towel off a roll. What keeps the roll there? Inertia. Turning clothes right side out by snapping them. You're using inertia again with that too. They tend to keep going. You yank on it, it tries to keep doing what it was doing. Okay? Any other questions? Just as you wander around doing whatever you do, watch inertia at play. Things continuing to do what they're doing. It's all over the place. All right. That said then, so now I'm going to start to flesh out what I started as Newton's first law last time. I didn't have the words to write out Newton's first law in its formal definition. It was simply the observation that an object that's free of external influences continues in motion, covering equal distances in equal times. That was the original version. We're going to build a better version, two better versions finally. The first one is how do you describe motion, basically? And I'm going to, over the course of the next some number of minutes, I'm going to come up with 5 what are called physical quantities. They're words that describe a specific physical thing. Some of them are familiar, some are not. Anyway, to describe motion, the skater who is left to themselves and basically just is coasting. You know, what does it mean to be coasting? A person who's coasting is moving according to inertia. That's really what coasting means. And what they do is they move at a constant speed in a constant direction. That's my short answer to this question. How does a skater that is coasting move? Constant speed, constant direction. So here I am, and I'm basically moving at constant speed. That way I'm covering. What does speed mean? It's how far you travel per unit of time. So for example, 3 feet per second is a perfectly good speed. So I was traveling about 3 feet per second. I'm not going to worry too much about metric versus English units. Really American units. We're pretty much left behind by the whole rest of the world with these funny units that we call English units or something. Anyway, so I'm moving about 3 feet per second, and I also am moving to the right. And that's quite different from this, which is 3 feet per second moving to your left. So we'll get to that in a sec. All right. So to start fleshing out the words, 2 physical quantities. The first one is not the one we want, but it gives us something to start with. Position is a useful physical quantity that tells you where something is located. And position has to have a couple of pieces of information to it. It's not just to describe where I'm located. You can't just use a number, and you need more. You need more. You can say, for example, that I'm 6 feet. It's a number like 6, and feet, which is what is called a conventional unit. It's a unit of measure, in this case of length. So I'm 6 feet, but that's still not quite enough information. 6 feet from where and in which direction? So I need a reference point. And the reference point that I've used for way too long is right between these two monitors, right there. That's the official reference point. That's position 0, okay, in my story. And I'm 6 feet from position 0. And we're sort of pinning down where I'm located, my position, except this is 6 feet from position 0, and so is this. There's one other piece missing, and that is the direction from position 0 to me. So I'm 6 feet that way, which happens to be south. I'm 6 feet south of position 0. And now you've really pinned it down. And the value of having done this is, in principle, you could call somebody up on the phone who can't see what's going on here at all and say, and tell them where I'm located now. He's 6 feet from position 0 south. Okay? The long and short of this whole harangue is, position is it's a physical quantity that has a couple pieces to it. It has the reference choice, and we all can agree on the reference choice once and for all and stick with it. In that case, it's that location. And the other part is an amount and a direction. The amount is a distance. It is a number and a conventional and a chosen unit of distance. So that it's 6 feet. Could be 72 inches. Could be a little less than 2 meters. And the other piece is the direction, south. So what long and short of this, I guess, is position is what's known as a vector quantity. You have probably encountered the word vector at least somewhere way back. A vector is nothing particularly sophisticated. It is a quantity that contains more than just a number. It is a quantity that contains at least a number and a direction. And for physical quantities, in almost all cases, not only is it a number, but it's a number and a unit and a direction. So that makes a full vector physical quantity. What's the alternative to a vector quantity? What's called a scalar quantity with an S-C-A-L-A-R, which is a quantity, physical quantity that has a number and a unit but no direction. For example, your weight. It's got an amount, it's in units like pounds, but there's no direction to it. And I should be careful with that because we'll talk more about weight shortly. It's a bad choice. But there are quantities. 1 cup, it has no direction to it. 2 ounces. Okay, so position. Questions about position? The idea that it identifies where something is, and it has a reference point, and it has an amount and a direction. Leave out the direction, you're in trouble. I mean, not like you failed a class. It's like you didn't specify the whole story. You missed something. Second physical quantity is velocity, and this is the one I really want. And the reason I define position first is because what velocity is the rate at which something's position is changing with time. For example, right now, my position is constant. It's not changing at all. So my velocity is 0. That shouldn't be any great surprise. But if my position begins to change like this, I have a velocity that's not 0. Every second, my position has moved over, in this case, to your right by about 2 feet. So end of story. I'll go back so I can talk about it. So my velocity right now is about 2 feet per second, but that isn't enough either, because this is 2 feet per second, and so is this. So lo and behold, velocity has a direction to it as well. So velocity, in this case, my velocity is 2 feet per second to your right. And now 2 feet per second to your left. So velocity and speed are not identical. Speed is how fast you're traveling. 2 feet per second, that's my speed. 2 feet per second, that's my speed. Velocity has an extra piece of information. So if you've equated those two words your whole life, this is a case where you want to separate them. They're different. Velocity has the direction part to it. In some languages, they are not different, and that's has been tricky in cases where I've done stuff and tried to translate it over, and they tell me, well, it's the same word. But in English, velocity has direction to it. Speed does not. And that matters if you're trying to go to Washington. You certainly don't want to have 60 miles an hour to the west. It's not going to do it for you. I mean, yeah, it'll do it for you if you want to drive for how many days is it going to take you to circumnavigate the globe. But you know, the faster route is 60 miles an hour, sort of northeast. Depends on whether you want to go home for Thanksgiving or not. All right. So you okay with velocity? And you remember the direction part to it. All right. So we can now improve the language for a skater who is free of external influences. They travel at constant velocity. That constant velocity has within it the whole idea of going in a straight line at a steady speed. The steady speed part is the amount of velocity. Speed is the amount of velocity. The direction of travel part is the direction of velocity. So in this case, it's to your right. This is 3 feet per second to the right. That's my velocity. This now is 3 feet per second to your left. Different velocity. Completely different velocity, same speed. All right? The little scooter stand is genius. It makes my life so much easier. For years, I have the thing falling all over the place. Then some students gave me this stand. Yeah. No, it's good. So velocity includes speed, but speed does not include velocity. That's correct. Velocity is a more complicated physical quantity. Speed is just one of those scalar quantities, no direction. Velocity is speed plus the direction. Yeah. Thanks for asking. So the question is when writing out velocity, do you use positive and negative? Positive, say, for the right, negative for the left. That's an interesting question because there are times when we will use the positive numbers to describe movement in one direction, and the negatives to describe it in another. And that works as long as we travel along a railroad track, basically. That is, we never deviate from a line. And there are motions like that. And so then just as shorthand, you say this is positive, which is equivalent to saying to the right, and this is negative, this is to the left. But in the grand world of 3 dimensions, it's more common to just give the direction full-blown. It's to the right, as opposed to the right and toward you a bit. We could pin this down more carefully, but why bother? Okay, so you give the whole thing. There are all these possibilities. You have to say them all out. And So this is to the right has all the information. To the left has all the information. There are times when we will say, I'm moving to the right at a negative speed. You can do this. I'm moving to the right at -2 feet per second. Right? I never did learn how to moonwalk. It's pretty sad. I'd love to be able to pull that off. You go, oh, he's cool. Anyway, you can laugh with me, you can laugh at me. I don't care. I mean, I care a little. But negative amounts of a physical quantity that has a direction are the same as positive amounts in exactly the opposite direction, and that will show up from time to time. It may seem kind of weird, but it turns out to be important. Okay? Other questions? Yeah. When I slow down. As I'm actually going. So this is an observation that I can't quite pull off inertia, right? Here, inertia would say I would go absolutely steady pace, straight line, truly constant velocity. The reality is there's friction in this damn razor scooter, and there's air resistance. And it's a nuisance, and this is one of the reasons why inertia was so hard for people to figure out right. And you sort of take it for granted, but you sort of don't because you don't quite believe in it. For example, it's pretty easy to have the sense that an object at rest stays at rest, fine, that's inertia. An object that you push on moves, and if you don't push on it, it stops. Your gut wants to believe what I just said, doesn't it? So that force we used a word ahead of time. Force is the fancy name, the physics name for a push or a pull. It is another vector quantity because a push to the left is different from a push to the right. So it's how hard you push and which direction you push. That's a force. We'll come to it in the next slide. It looks like a force causes velocity. Absence of force, velocity drops to zero. Sure looks like that. And people, very wise, smart people, approximately Aristotle and gang, thought that that was the case, that forces approximately caused velocity, and that when you stop pushing, things stopped. The problem, of course, is friction. If you get rid of friction, which is hard to do along the Mediterranean unless it's very cold and you get lucky, but with modern gadgets, I can get rid of most of friction. This is now sitting on it's an air puck. It's got a little fan inside that's humming away, and it's sitting on a cushion of air. And this guy, I'll bust it, I'll knock, this guy, if I give it a push, inertia, straight and true, pretty much the whole way across the room. Because now this thing can pretty nearly exhibit inertia. That if you don't push on it, it stays put. But if you push on it, it changes motion, and then it moves for free. And now the table's not very level, so this is imperfect. But if we could get rid of friction, and I can't do it in the Razor scooter, I mean, it's hard to get. If you really got rid of friction, and I got started, I would go exactly straight at an exactly steady pace forever. This does show up in modern life in the form of the travel of spacecraft. Two spacecraft, for example, I don't know, the space station and an astronaut not connected to the space station. They are two independent objects. And there is gravity around, which is another story. We'll come to it later. But for the you can sort of imagine gravity is of no consequence, which is a bit of a swindle. But it's pretty close to no consequence. They will just move according to inertia. And if they had the same initial velocity at the time the story started, they'll keep having the same initial velocity. And that's why an astronaut and the space station, the spacewalking astronaut and the space station, they travel independently according to inertia. They're going really fast. Have you ever paid much attention to what's going on with rockets, and we'll get there, that's later in the semester, they're traveling at miles per second relative to us. Woo, okay? And they're both going approximately straight and true because of inertia alone. And spacecraft, there's so little bothering a spacecraft that some of these ones that have really gone out into deep space, the Voyagers, for example, they're basically coasting at constant velocity, steady pace, straight line, and they will do it, apart from tiny little perturbations due to gravity, to the end of time. They're off. All right? So modern people have been able to see inertia really at play, where it's almost perfect. Other questions? Okay. So having developed the language of position and velocity, we can write Newton's first law in its second version, which is that an object that's free of external influences moves at constant velocity. Whatever velocity it had at the start of the story, it has at the end of the story. Straight line, steady pace. That's what a constant velocity is. And I've got in yellow there the idea that physicists do this. They talk about a velocity of zero. It's moving with a constant velocity of zero. And you might go like, but it's not moving. Well, physicists say it's moving. It's just a very boring moving. Zero. All right, questions about that idea? So this is really what inertial objects do, or sometimes I refer to it as inertial motion. Motion completely dominated by inertia and nothing else. It does what it was doing. Its velocity remains constant. Zero being a possibility. It's moving to the right, it moves right. Moves left, moves left. Okay. So now the word that I brought up earlier, I'll bring it up for real, force. If we want to look and see what happens when, what are the external influences? In this context, what are the external influences that we don't want in order to be inertial? We don't want external forces, which is to say we don't want external pushes or pulls. So a skater, so for example, me again, just to go back to this issue of why did I slow down, the reason I slowed down is because I can't quite get rid of the forces pushing me to the left. I was heading to the right, and these nasty troublemaking things like friction and air resistance both push me to the left and remove my rightward velocity. So if I could get rid of those, I would keep going straight and true forever. Questions? So, because several forces can simultaneously gang up to push on the same object, the object can't be affected by each one individually. It's affected by their sum. So if 5 people are fighting over you at a I was going to say cocktail party, but I guess they're back in vogue, aren't they? Right? Anyway, at a root beer float party. 5 people are fighting over you at a root beer float party. They all want you to go with them. You don't, well, unless they pull really hard, in which case drawing and quartering comes to mind. But if you're pulled up suitably, you respond not to the individual pulls or pushes, but to their sum. And the sum takes into account which directions they're acting. So 2 people fighting over you, each pulling one to the left, one to the right, typically those 2 forces kind of kill each other off. If they're both pulling you to the right, they help each other. They sum to a larger rightward force. And first of all, the sum of forces, taking into account their directions, is known as the net force, just like net income. And the word net is taking the usual meaning. The sum involves the directions, and therefore it's what's called a vector sum, as opposed to just adding up the force strengths. And you have to take the directions into account, and that's the kind of thing that a conventional physics course would dwell on for days. And I don't care to do that. I don't think you want to do it either. So common sense will lead you into understanding most of the story with respect to vector sums. So the point of this is now that we can now say Newton's first law in its real form, the final version, which is an object that's not subject to any outside forces, or equivalently to, or not equivalently, but if the outside forces are there but they sum to 0, same thing. So basically there's no net force on an object. It's inertial. It moves at constant velocity. All right? So when I'm doing this, when I'm tootling along on this razor scooter, I'm actually subject to a whole bunch of forces that I just can't do without, one way I can't get rid of. There are the ones that are fairly important, like gravity is pulling me downward, and the floor is pushing me upward. And fortunately, those 2 cancel. So that's something we'll deal with shortly. So I'm getting pushed down, I'm getting pushed up, I am being pushed backward a little bit by friction and air resistance, which is a nuisance. But if I could get rid of those, even though I'm being subject to a bunch of forces now, they would sum to 0, net force 0, and I'd be inertial. I would coast. All right? So that's the whole story of Newton's first law. All right. I'll get it later. So a skater spends a lot of their time inertial, all the forces canceling, and therefore moving as inertia and Newton's first law had in mind. What if they don't want to be inertial? What if they want to start moving or stop moving or turn? In that case, they do want some overall net force acting on them. If they experience a net force to the right, they will begin to move faster and faster toward the right. If they experience a net force left, faster and faster toward the left. And if they experience a net force, say, let me do it. If I experience a net force to the right, which I'll do right now, here, ready? It's that net force to the right, it's over. But I picked up speed toward the right. How about net force to the left? Here it comes. It's coming out of the ground. My foot's doing this. My foot and the pavement are playing footsie. Here we go. So I picked up speed to the left. And if I develop a force toward you, which I'll do with the front wheel of my little scooter here, I change my direction of travel. So in every one of those cases, the cause of something interesting happening is a force, particularly a net force, an overall force. And the consequence of that force was a change in my velocity. I was no longer moving at constant velocity. Something else happened. The name for a change in velocity, or really the rate at which velocity is changing with time, is called acceleration. And this is a word, you know, again, you've heard it forever, but it's not trivial to understand well. And so I want to take a few seconds, more than a few seconds, to help you understand acceleration. It was also one of the first, you remember I had those pairs of words, how well can you distinguish these? That was Wednesday. I asked you, how well can you distinguish velocity and acceleration? They are not easy to distinguish. You've got to think about them. It's a learning process. So let me show you acceleration in a couple of forms. I'm going to accelerate to the right, which is, remember, well, I should be real clear here. Acceleration is the rate at which velocity is changing. So let me show you no acceleration. Here's no acceleration. My velocity is 0, still 0, still 0. Okay. Now, I'll show you another version of that same thing. Don't watch yet. I got to get started. Now you can watch. My velocity is to the right 2 feet per second, to the right 2 feet per second, to the right 2 feet per second, to the right 2 feet per second. End of story. That was a whole stretch of no acceleration again. Right? My velocity was the same. There's no rate of change in my velocity. But now let me show you some acceleration. First, I'm going to accelerate to your right. And each of these physical quantities has units. And the units get more and more complicated. Position had units of length, how far you are from something. Velocity has length per time, how fast you're covering distance. Acceleration has length per time, or, for example, meters per second squared. Units, we could, again, dwell on units for for the whole season here. Hopefully, you'll pick some of the unit issues up, but it's not something I'm going to beat on. So I am going to accelerate to the right at about 1 foot per second per second. Here we go. Ready? Get set. End of story. With every passing portion of time, my velocity increased toward the right. That's what acceleration is. It's a change in velocity. So I was going faster and faster toward the right. If I reverse the direction of acceleration, it's another vector quantity. If I reverse the direction, 1 foot per second to your left, same thing. Whoa! Okay, end of story. One of the observations that I've made recently that seems useful, at least to me, is that to observe something's position, you need to glance once. Just blink, you know where I am. If you want to see what my velocity is, you have to glance twice. Glance, glance. Oh, he went from there to there, and we know how long it was in between. We figure out how fast he's traveling and in which direction he was going. So velocity takes 2 glances. Acceleration takes 3 glances. You got to look once, blink, twice, blink, 3 times. Ooh, he went farther during the second pair of blinks than the first pair of blinks. He changed his speed. He went faster. So acceleration is a 3 blink measurement. Okay? More about acceleration. I'm going to show you my acceleration with my hand. My velocity is pretty easy to follow. My acceleration is not so easy to follow. So this is no acceleration. This is acceleration to the right. This is acceleration to the left. And I can do, sometimes on a good day, I can do 1 thing at a time well. 2 things at a time well. Whoa, no. Okay, so I'm going to try to pull this off. So I'm going to accelerate. Here we go. Accelerate to the right. Now I'm coasting. Now I'm going to accelerate to the left, come to a stop, and now stop. And I'm stopped here forever, right? Okay, I'm going to accelerate to the left. I better stop. I better stop accelerating, but I coast. Whoa, come to a stop. And then I pick up speed this way. Okay? So among the things that happen during this kind of insanity are times where I'm heading to your right, but accelerating to your left. Let me show you one of those. It hasn't happened yet. Ready? I'm going to get started. Okay, I'm picking up speed to the right. I'm now going to accelerate to your left while moving to the right, and I come to a stop, and then I overshoot. So during this rewind to tape, there was this period where I was doing this, whoa, like that, right? I was accelerating to your left while moving with the velocity to the right. Basically, I was losing my rightward velocity. It was shrinking until finally it got to 0, and then it became backward. It reversed directions. And then I started picking up speed towards your left. So we have a special name, a familiar name, for this process. You call it deceleration. Deceleration is just a special case of acceleration, where you're accelerating in the direction opposite your velocity. You're losing that velocity. So when you hit the brakes on a car, it's also this is like this. How many accelerator pedals are there, or accelerator devices are there in your car? There are 3 of them. There's the familiar accelerator. When you push on it, right? That's acceleration in the direction the car is heading, right? So the familiar accelerator pedal is a forward accelerator in the direction the car's aimed. The brake, that's an accelerator pedal backwards. It's causing you to decelerate or to accelerate in the direction opposite your velocity. The third acceleration device is the steering wheel. Why? Because I've been showing you accelerations so far all along that railroad line. We mentioned earlier the positive and negative stuff. You can say that's positive, that's negative. But what about this? There's my velocity. I'll point for once in the direction of my velocity. Man, it's constant in length. That is, my speed isn't changing, but my direction of travel is changing, and I'm getting dizzy. And that is an acceleration. If your velocity is changing, I'm going to stop. You guys stop too, please. Okay. If your velocity is changing in direction, you're accelerating as well. That counts, totally. So the steering wheel of a car, which changes which way its path, does indeed cause accelerations of the car. And those accelerations, it turns out, are caused by a net force in the car. It's coming from the pavement. But on an icy day, when you try to steer on ice, sometimes it doesn't work. You don't get those forces. And instead you travel inertially, which is, say you go straight. And so, suppose this is an icy path here. So icy that I cannot get any frictional forces out of it at all. And let's get rid of air resistance because it's just a nuisance. Let me get started somehow in my car. So I'm heading off and straight and true, and I want to turn to the left. I turn the wheel, but no forces come. Bang! What happens then? On an icy day, when you try to make a turn with the road, no forces show up to cause you to turn. You travel according to inertia. You go straight and true. And people, what I'm thinking of, what I have in mind is like a homework or an exam question. The road veers toward the left. Which side of the road do you go off of on an icy day? If the road veers to the left and you go straight, you're going to go off the right side of the road. Can you picture that? This is what happens. So when they say steer into the skid, what you're trying to do is you're trying to get the wheels to travel, to roll in the direction that inertia is taking you. Because that's what's happening. Inertia is governing the motion. You want the wheels to begin rolling again. Another topic, that when they're rolling, they're more effective at steering you than when they're skidding. So you want to aim them in the direction that inertia has in mind, because then they will begin to roll again and become useful. All right. acceleration. Got a reasonable feeling that you can separate acceleration from velocity? They're not the same. Acceleration, you've got to look carefully to see how velocity is changing with time. And any change in velocity, whether it's in the speed or it's in the direction of travel, any of those is an acceleration. They're all caused by forces. Well, that leaves one other important physical quantity, and that is not all, it has to do with the following observation, that not all skaters, suppose you got a whole bunch of skaters on the ice arranged so that they're basically inertial whatever you do, and you go and you give them all equal shoves. And the little kid skater, you give them a shove, whoosh, and they pick up speed dramatically. They accelerate easily. Of course, their acceleration is in the direction of your force. That's something I should point out. Forces cause accelerations, and those accelerations are in the direction of the force. You push something to the right, it accelerates toward the right. It's an observation again. If you push something to the right and it accelerates to the left, that would be a big surprise. You've never seen that happen. So you give them a push to the right, off they go. But the little kid accelerates more easily than the great big sumo wrestler. Nope. They accelerate, but it's a long slog, a lot of push, not much change in velocity. So there is a resistance to acceleration. Forces cause acceleration, but the given object has a tendency to resist the acceleration. And that is basically, it's how different objects have different sort of amounts of inertia. And the measure of an object's inertia is known as its mass. So that's where I'm heading, the word mass. Again, another word that's familiar, but here's the real meaning of mass. It is the measure of an object's inertia and how hard it is to get that object to accelerate. So the little kid has a small mass, the big sumo wrestler has a big mass. Same forces applied to those two will cause different accelerations. And the acceleration of the objects is proportional to 1 over their mass. Double their mass, you get half the acceleration. Mass, of the 5 quantities I've now introduced, mass is the only one that is a scalar, no direction to it. It was the better choice. Earlier I mentioned weight, bad choice. Mass is a better choice. It has nothing to do with direction. It's just an amount, the extent to which an object resists acceleration. So here is Newton's second law, and I'll leave Newton's third law for a couple days. But Newton's second law is a beautiful quantitative relationship between force, mass, and acceleration. And I'm writing it the way I prefer, which is to say, an object's acceleration, drawn there as an equation on the left, is equal to 2 things. The net force causing the acceleration divided by the mass resisting that acceleration. So if you have a force and you apply it to a skater of a certain mass, you can figure out what acceleration you will cause by dividing your force by the skater's mass. The bigger your force, of course, the greater the acceleration. The greater the change, the faster the person will change velocity. So also, the more mass the skater has, the slower the change in velocity. So that's why I've written it as acceleration, which is the end result, is equal to force divided by mass. The force that causes, the mass that resists. All right? That's as opposed to the traditional form, which for a great many of you, you've had a year of physics, and you've encountered it written not as my version, but as force equals mass times acceleration, which confuses cause and effect. It doesn't have a division in it, so it looks prettier on, for some reason people got all upset about that division and said, nah, I got to get rid of it. So we play algebra games and get rid of the division. But this has got here's the cause, net force, is equal to a mixture of the result and the resistance to the force. It's to my mind, logically unpleasant. Mathematically equivalent, but it's not as clean. All right? So the point of all this is, if you have, getting rid of all the other forces in the universe. If you push on something with your force, and you know how much mass that something has, you know how it's going to respond. It will accelerate, and its acceleration will be your force divided by the mass in the direction of your force. Okay? So skaters are doing this all the time. Often, sometimes they're pushing on each other, short track racing being an example. But mostly they're being pushed on by what? Well, by the ice. They're doing things like digging their feet into the ice in various ways and summoning a force from the ice onto them. And we can get into that. It's basically friction. It's a friction effect. Skates, I'm picturing ice skates, and roller skates too. They're smooth running one direction, but across the skate they don't go so smooth. They get a lot of friction. And so you can get forces out of the ice if you're clever. And those forces are what cause a skater to pick up speed, to come to a stop, or to turn, are those various horizontal forces. All right? So I've got a bunch of cans here. So here's one of my questions. There's a bunch of cans there. Some of them are full, some of them are empty. How can we distinguish one from the other? Yeah, D, of course, is a perfectly reasonable. It's got a 50-50 chance of being right. So we can compare the velocities of the cans, we can compare the positions of the can, we can blow on each can and observe its acceleration. How many think A? How many think B? How many think C? Thank you. Oh, I'm D, yeah. Okay. The Coke cans are both empty. And what was the measurement I just did? I exerted forces, horizontal forces on all 5 of them, approximately the same force. It was really the only important force they were experiencing. So they all accelerated in response to that force. Well, the Coke cans, being empty, had very little mass, and they accelerated like crazy, and off they went. The other cans, the brisk cans, being full, have far more mass, are much more reluctant to accelerate. And off you go. Okay, so this is a goofy example, but another example is things that have where you encounter, for example, a rolly cart. I'm picturing the luggage wagons they have at the airport. Those wagons, they're closed in various ways, so you can't see. Does this one have luggage in it or not? They're too heavy to lift, so you can't do that, which is a different kind of measurement. But you can shake them, and if you shake, you roll it forward and backward. The empty one is going to be easy to shake because mass is the resistance to acceleration. The shaking process, like this. This is velocity to right, velocity left, right, left. This is acceleration. I'm doing lots of acceleration, right? If you shake a container, the wheels support the weight of the container, so that's not a problem. But if it shakes easily, it has very little mass. And therefore you know that it doesn't have luggage in it. The one that's full, oh my gosh, can't shake this. It's full. So this is how you measure mass. As a last aside, astronauts, it's very hard. You can't weigh an astronaut. We'll talk about weight next time, whatever. But you can't just put them on a scale and try to measure them. How do you figure out how much astronaut there is after a long space voyage? And you want to know, has the astronaut fattened up or thinned out? What do? Shake them. So they've had over the years gadgets on some of these spacecraft that the astronaut would grip very tightly so that they're really held in place nicely by this frame. And then the frame shakes them. Push them forward, pull them back, push them forward. See how hard it is to make them accelerate, from which you can derive their mass, their resistance to acceleration. Okay? We'll continue with falling balls then on Monday.